All right. Yes, the audio's on. Beautiful. Let's adjust this. Sure. Let's go back. And let's find my problems. Okay. All right. So this is actually section 8.2. Oh, hold on. Am I on the wrong side? Yeah, why can't I get the orientation of this right? Yeah, I'm on the wrong side. Hold on, y'all. Hmm. All right. So we're back. And this is actually section 8.2. So we're jumping from, we were working chapter 5 last week. We're going to jump to chapter 8 because this is another chapter just purely about integration techniques. So like I was saying towards the end of that last video, we're going to stick right now just with integration techniques. And then actually that'll take us through to your first test, or since it's a 5-week class, your midterm. So that'll be next Thursday, by the way. So again, not this week, but next week. And towards the end of this week, I'll send out a message about that to y'all. But yeah, so we're just going to focus on just purely integration techniques, just doing the thing abstractly. The rest of this week and through that first test. And then after our midterm, we'll go back to applications of integration and look at finding areas, all that kind of stuff. All right, good. So, anyway, so we're looking at 8.2. And so on the last lecture, we were looking at substitution or integration by substitution. Substitution is a way of doing intervals. So we want to look at another, I would say, incredibly major technique that we have for integration that is going to cover a lot. So integration by substitution kind of covered a lot of problems that you could see, a lot of functions that you could see. Another one that covers a decent number, a lot of what do you call it? Integration problems you can see is integration by parts. So that's what we're going to look at today, integration by parts. And to kind of get you into not only what this is, but why we're doing it, let me write it up there. So give me a second. Let's see, which one of these? That's kind of so it's on my and here we want to take the integral. X e to the 9x. So we want to take the integral of something like this. And so the first thing that I want you to notice that I want to talk about, so just the first thing that I want to get y'all to think about is, so looking at this problem, does this look like a problem where you would use substitution, integration by substitution? And maybe or maybe not for you, but hopefully thinking back to what we just did. So when you see this, you may look at this and be like, that's easily integration by substitution, right? It's two. So some of the things you saw pretty consistently for integration by substitution, we saw two functions multiplied together. And we just basically needed one, we also saw sort of one function plugged into another, right? So you see that here, you see a 9x plugged into an e to the x, and you have kind of this other piece or this other function outside. With integration by substitution, the kicker was whatever was outside had to be the derivative of what was inside, so that we could kind of play the game, do the substitution, and have it work out. You know, so again, so your u is whatever is inside, we take the derivative, and what's the derivative should match what you see outside. So I want to test that here. So 9x seems to be what's inside, that's plugged into the e function or the exponential function. What is the derivative of 9x? Good, that's 9. And notice that 9 is not x, not an x. 9 is a constant, and this is a variable function. But even more than that, I mean, yeah, so I mean, it's not just that the derivative, this is 9, and I don't see it here, but this is much different. And so if you think about functions kind of like this, where I have basically one function multiplied by another, it would be nice if everything worked out like substitution, that the function outside was the derivative of sort of the thing being plugged in inside. But as you can maybe visualize in your head or just think through, it's easily possible. It's going to happen very often that this function outside, or it's just easy for this function outside not to be the derivative of the thing inside. And so if it isn't, then we can't use substitution. And so then the question is, well, if I can't use substitution, how do I go about this? Now, when you were doing Cal 1, so I want to pause this for a second. When you're doing Cal 1, let's say I had something like, I wanted to take the derivative of, I don't know, 5x squared times cosine x, something like this, right? Or I don't want to make it too like the problem that we're looking at, because I don't want to make, you'll see, I want to make a general connection, if not a direct connection here. But let's say I wanted to take the derivative of something like this. So I want you to think about it really quick. How would you go about doing this? In fact, let me actually have you play this out for a second. So just not only to jog your memory, but to really connect with what you did in Cal 1, and hopefully then be able to connect to what I'm about to show you. I'm actually going to give you a second to go ahead and do this derivative. So pause on your side, I'll pause on my side. See if you can do that really. So if you want to take the derivative of that, so remember that here we have a derivative of two functions multiplied. And again, hopefully one of the main things you took away from Cal 1 is that there's a pattern for that. And that pattern for that called the product rule, but it was just basically, if you think of this as one function times another, then it's the first function times the derivative of the second, plus second times the derivative of the first. So this one would be 5x squared times the derivative of e to the x, which is just e to the x, plus the derivative of the second, 10x, times the first, or sorry, the derivative of the first times the second, which is 10x e to the x. And that's our answer. You could be fancy and algebraic and factor out a common factor here, but honestly, that's just for the sake of books and, getting you to keep practice simplifying. Mathematically, sure, that's fine. You could play this game, do a little factoring, that's fine. But good. All right. So the reason I'm doing this, so we kind of have two functions we're taking the derivative of. And we end up with something like this, which also can be written like this. So notice that you end up with one function in front of that e to the x, or one function multiplied by the e to the x. This function does have a plus there, so this is where I'm saying I don't want to make a direct connection to what you're seeing here, but I want you to then consider what we're doing here. So we're now trying to integrate something that is one function times another. So what I'm trying to say is, in general, the fact that the derivative of this kind of gives you one function times another, then there's at least an instinct that if I want to integrate this, so if I see this as sort of the end of a product rule, then I should be able to work my way back up. Now, again, it doesn't have the plus, which I admit makes it kind of look like not, look like it didn't come from a product rule. But broader, the idea is if I'm trying to integrate something that's one function times another, and like we just saw, substitution is not going to work for us, then there's at least there's at least the hint or the idea that the thing that I'm seeing is the end result of the product of two functions that were originally multiplied together. Well, I can't say, maybe not two functions that were originally multiplied together, but anyways, the end of the product. And so if you take a look in this section again, because it's a 5-week class, I'm not gonna go into proving it, but if you take a look in the section, they actually show you, they show you, so this 8.2, they show you that there is a way to prove that not just for this function, but just in general, when you have something like this, that basically if you run product rule in reverse, you can find a way to integrate this. That's maybe the larger connection I'm trying to get stressed. So again, the hints are you got two functions multiplied, and substitution doesn't work. So that's actually, again, you see this problem randomly on your test next week. What I'm saying is try substitution first. So when you're kind of think about kind of integration as a little bit like a check down procedure. And the first thing you actually want to try is substitution. But if substitution doesn't work and you have two functions multiplied together, then integration by parts is sort of your second check. It's your thing to go to see if it'll work. And like I said, integration by parts, at least theoretically, concept-wise, is essentially backwards. What do you call it? Backwards product. So let me kind of show you how integration by parts works. So the actual kind of playing out of integration by parts, the way this works is they're going to say, so what you want to do is you want to, the integral of u dv equals uv minus the integral of b from u. So the idea here is you want to take the integral that we're looking at. Again, we're trying to say that it's sort of the result with some extra pieces added, but it's the result of, it's sort of the result after product rule. So you're going to look at the integral that we have that we couldn't use substitution with, and you're going to basically declare one of the parts to be u, and then the other thing here is we got to declare one of the parts to be dv. So one of the parts is sort of the derivative of this fancy function v that we haven't identified yet. But once you do that, so we got to code one of these as u, one of these is dv. Once we do that, then you're going to see we're going to go and figure out sort of what v is, number one, and we're going to figure out what du is. And again, they prove using product rule in this section that every single time that if you identify one as u, one as dv, then the integral of this is this automatically. So it kind of works theoretically, it works concept-wise, it works in the abstract every time. So again, you run across one of these problems, you try substitution first because it's two functions multiplied, but you can't make substitution work, then you're going to try integration by parts. And so to do this, I'm going to identify one of these as u and one of these as dv to start out with. I think the thing that we'll see, or the thing that you'll see doing these problems is that in some problems, it doesn't matter which one is u and which one is dv, but in a lot of problems, it really does matter. So as you're doing these, we're going to practice some of these and then you're gonna get to practice more on your homework. Because really, the only way to get good at kind of picking which one is U and which one is DB, is a ton of practice. There's some pretty good guidelines that I'll talk about as we do some of the problems today in this lecture. But honestly, beyond that, it's more of a gaming thing, right? So it's like you gotta play the game multiple times to get a good instinct on which one's better as U and which one's better as D. So let's start with 5 here. And what I'm gonna do here is, so when I pick U and DB, I do have a couple guidelines going in my head that I've developed after playing this game quite a bit, a lot of times. One of the things I noticed about this, so I want to talk about kind of again this pattern, this setup. Give me a second too. I'm thinking too fast, too far right now. So I would say one of the things that I hate about integration by parts as far as the way it's laid out to you is they just give you a formula, right? So integration by parts, they give you this formula. They say, integral of UdV equals UV minus integral of VU. But so thinking about it as a formula is really actually not a great way to like think your way through what we're about to do. Because it becomes this game of like, here's a U, here's a DB, like you just gotta like basically identify pieces and then do some stuff and plug it in. And it doesn't really tell you again how to get through or think through the problem. So I think of integration by parts not as a formula, but sort of as a journey, as a process, as a procedure, right? So and the procedure is, again, like I said, the first thing is you're picking U and DB. My guidelines for picking U and DB. So you pick U and DB so that you can get to the right side here, so that you can kind of take a journey of transformation from what I pick from U for U and DB to what I see on the right side here. And part of that journey, part of that transformation, and what makes, I would say, actually integration by parts different than some of our other integration methods is notice that what my formula, but really what my journey is saying here is I'm starting with an integral. And I'm trying to do the thing. I'm trying to do what an integral does, which I'm trying to find the function above it, that when I take the derivative, I get this. But the interesting thing about integration by parts that doesn't happen with any of our other techniques is the answer is, yes, it's a function. That's what we'd expect to find. So again, normally integration is a journey up, right? It's a journey to what is the function up here that when I take the derivative, I'll get down here. So yes, I get a function, but then I get another integral. So basically, to integrate by parts, it requires you to do another integral sort of at the end. So you get a function, but you get a function with a comma, right? You get a function with a semicolon. You get a function with a but, basically. Like it's this, but you've also got to figure this thing out. You've also got to do this. So again, this is why I kind of think of it as a journey. I want to get back up to the function, and I get a function but not completely. I get a function, but I also have to take the integral of v to u, so I got another little journey to go on. I gotta figure out what function, when I take the derivative, gives me the integral of v to u. So there's a little bit extra process there. Because of that, because I know that that's the end of my journey, when I pick my u and dv, really the thing that you're worried about here is this v to u. So UV is, again, the answer, comma, but I've also got to be able to take the integral of V to U. And so the kicker here is always, I want to pick these in a way that this is easy to do. And if I don't pick this and maybe, just if I pick this in usually it's the opposite of what it should be picked, then that's what you'll find. That's actually the kink you'll find in the process, or kind of the thing, the signal that tells you to kind of turn your picks around. That if you don't pick this in the right way, then this becomes either hard or sometimes actually impossible to do. So if you find this integral being hard and impossible, that means go back and kind of switch your hits. So I'm looking at these two functions here in 5, and I'm basically trying to figure out which one is u and which one is dv, to make this part easy. Now notice that So to make this part easy, notice that whatever you pick for u, you're putting the derivative here. Whatever you pick for dv, you're putting that original function. So this is my qualifications, or the way that I think through the pick that I'm doing here is that's actually like so the way I pick this is I make sure whatever I'm picking for u here, the derivative, I can take the derivative, and the derivative is easy. So basically that's one of my qualifications in my mind. I want the derivative to be easy because in some sense, you want this integral to be easy to do, right? You want it to be simpler than the integral you started with. You can think of this almost like a Russian nesting doll, or like some sort of nested path. So I'm starting with an integral that I can't do. Like we said, we try our normal method, substitution, we can't do it. So this integral is harder than normal, quote unquote. And I have a journey, a process where then I transform this integral into this. And what this essentially does is it allows me to get away with doing this integral by just having to do this integral. So this process is nice because it basically replaces a more complicated integral with a simpler. But that's what you want to make sure. You want to make sure this is a simpler integral, which means my du should be simpler than my u. It also means that my dv, whatever I pick for dv, so again, in this integral, I'm going to be using v. So I want to be able to take the integral of dv pretty easily. And two, I want whatever dv is when I take the integral, I want it to be not more complicated, or not much more complicated than dv. So again, so internally, when I'm thinking about what is u and what is dv, pretty much that's my guidepost, is this needs to be simpler. So du needs to be simpler. V, because you're taking an integral, is by necessity going to be a little more complicated, but it should only be a little more complicated. Overall, I need this thing to be a lot simpler to deal with than my original integral. Okay, so maybe that was a lot of talking, and me saying the same thing over and over again, but maybe hopefully that connects for you. That's kind of the way I think of this. So for instance, on 5, when I look at this, I would automatically pick x as u, because I know the derivative of u. So what is the derivative of x? The derivative of x is 1, or just dx, and that is hella simpler than x. That's going to make this integral a lot easier to deal with. And also, if I pick then e to the 9x as my dv, I'm going to take the integral of e to the 9x. Is that a pretty easy integral to do? Yeah, it's actually pretty darn easy. And the integral of it. So you can think, you don't have to have the full answer or the completely correct answer, but just think about it in general. What is the integral of e to the 9x? Good, it's going to be an e to the x function, which is again going to be not much more complicated than what you see there, and it's going to be pretty darn easy to deal with as an integral. So by picking u as x and dv, or e to the 9x as dv, I've made this integral pretty easy to deal with. I'm going to be integrating an e function, and then du isn't even, it's just going to be dx. That's going to be really easy to do. So in general, that's, I would say, like in the section, they give you kind of a couple guidelines where it's like, try this, and if that doesn't work, try that. I'm not saying like trial and error is still a good play for integration by parts, but yeah, the guidelines I would give you is more something like that, of think forward to what you're going to have to do, and what you're going to have to do, the integral you're going to have to do is going to have to be easier than the integral you started with. So pick your u so that it, when you take the derivative, becomes something ultra simple, and pick your dv so that when you integrate that, you end up with something not much more complicated to begin with, and something that you can easily integrate. Good. So here, u is my x, dv is my e to the 9x. Actually, so dv technically, by the way, is actually e to the 9x dx. So that would be, after you take the derivative, you have that dx thing. So now that I know those, like I asked you, and you guys said, so if u is x, then the derivative of that, so du would be dx. And now let's get an exact here. What about b here? So when you take the integral, so basically you just want to integrate this part, so that's what we're trying to do here, let's do a little side work. Um, so we need to do the integral of e to the 9x dx. And yeah, go ahead and take a second to do that if you haven't already. I won't even pause, we don't have to pause, just take a second to do that. All right, so what do you guys get? Good, so when you take the integral of this, notice this is technically a little bit of substitution. This is a 9x plugged into an e function. So the integral of e to the x, or e to something, is e to that something. And then here we're just going to divide by whatever the derivative of 9x is. Or sorry, that's not substitution, it's just a little bit of kind of reverse chain rule. Or well, yeah, technically substitution. Anyways, so you should end up with e to the 9x over 9. Keep writing the 9. Good. So you pick your u, you pick your dv. Second step then is figure out your du and your v. And then what we're going to do is we're going to start filling in this. So my integral then is going to be uv. So u was x, v is now e to the 9x over 9 minus the integral of v du. So 1/9 e to the 9x. And then du is just dx, so we slap a dx on there. And now I have to take the integral of this. But again, notice that by making some smart choices to begin with and really just thinking forward in my problem and what I'm going to have to do in a later step and making that as easy as possible. Notice that this is actually really easy to deal. This is again technically substitution, but it's technically substitution, but it's really easy. You guys were doing this like section 5.1 and 5.4, no problem. So we need to work this integral out. So I'll give you guys a second to go ahead and do that. And again, I won't even pause because I don't think it'll take you guys long, especially if you just did this. But anyways, it won't take you long. So just I'll pace back and forth, take a second and work that integral. Let's see what goes. So what did you get for the integral on this? Good. So again, basically 9x is being plugged into an e function, so the integral is going to be the e function, but again divided by 9. So overall, what we should get here is 1/9 x e to the 9x. That's the uv part. Then minus 1/81 e to the 9x. All this plus c, so this is an indefinite integral. We're not integrating from one place to another and finding area or anything like that. And that's your answer. So the integral of x e to the 9x there's this. And again, like I was saying to begin with, so sort of the lesson at the end of this is if you took this, which would take you a little bit of a second, but if you took this and you did the derivative of this, you would have to use the product rule, but it would actually get you down to exactly what we started with, x e to the 9x. So integration by parts is sort of reverse product. So we saw substitution with reverse chain rule. Integration by parts is sort of reverse, sort of reverse product. So I think I said that at an earlier lecture that that's what you'll end up seeing. All those patterns you learn for derivatives in Cal 1, there essentially is usually a pattern for integration that reverses. But that's integration by parts. So the nice thing about this, like I said, is it's this pattern every time. So basically, like I was just saying a couple of minutes ago, we just need to practice. There is actually no other special thing to this. We just need to practice quite a few things. So this lecture will be shorter than the others because that's all we really do. So let me go find a couple more for y'all to reference. So in terms of our practice problems, let's start with. Let's try this again. Just give me a second. Actually, make sure it's working well. Actually, no. So let's keep it like the one in the book. So this is actually 25 in the book. Yeah, it's just over there. This is the integral of x times the square root of x minus 5 dx. And notice again, this looks like, what do you call it? This looks like several of the integrals we saw in the section where we were focusing on integration by substitution. So again, just kind of think through what if you see this on the test and the first thing is we think it's substitution, what would that substitution be? So let's again not be afraid to fail this. I just promise you a lot of these are going to look like substitution. So we want to try substitution first, and then when that fails, then your next check down is integration by parts. So what would the substitution be here? Just if you think this is substitution. Good. So hopefully you see, again, this looks very much like some problems we did in, what was it, 5.5. Square root is the sort of the overall function. So it looks like we're plugging in x minus 5 in there. But like our last problem, the problem here is that the derivative of x minus 5 is a 1 and 1 is not an x, right? So again, that tells you, so it's no problem that you think it's substitution to begin with. You try it and you don't like it. You try it and it doesn't work. So you realize this must be integration by parts. Kind of have just a higher power, higher level function outside than just the derivative. Good. So this is integration by parts. So let me have you guys kind of then practice solve this lesson. So you need to identify which one's u, which one's dv. Again, your goal is that your integral should be a good bit easier than your original integral to do. So let me see if you guys can work through this one. Pick those pieces and work the rest of it. So go ahead and pause on your side. I'll pause on my side. So I need to pick a U and I need to pick a DV. And again, my goal in my picks is I want my U. I need to do a DU with that, so I want that to sort of be easier. Or at least hope it's easier than my original because I want this integral to be easy. And then with the DV, similar idea. I want the B that comes from that, from the integration, to be, even though it's going to be more complex, maybe not that much more complex than the original. So looking at these, one possibility is to make this your U and this is your DV. But notice if this is your DV, then when you integrate, that's going to be an x squared over 2. We're going to end up with an x squared over 2 times, the integral of this is going to be 1 over square root of x minus 5. And you just end up with something a bit more complex. So the better pick here, kind of like we did on the last problem, is to pick x is my U, and then this is my DV. Pretty much anytime you can, it's a good, not just instinct, but just practical things. Anytime your x can be a U is very nice because du is going to be dx, it's going to be a 1. And that's almost always automatically, not always, but almost always automatically going to make this integral on the back end a lot easier to do. So we'll go that way. So that's my u, which means my du is just dx. That's fine. Now here, if this is my dv, I need to do a little work. I got to take the integral, the square root of x minus 5 dx. And to do that, then I am really going to have to do a little bit of substitution here. So this integral, what I see here is this is a x minus 5 plugged into a square root function, or basically to the x to the 1/2 power. So this is an x minus 5 plugged into a power function, just my power being 1/2. So when you integrate that, that power is going to bump up to 3/2. And then I'm going to divide both, I'm going to divide by the 3/2. Also going to then divide by the integral of the x minus 5, which is 1. So luckily that doesn't do much else for me. So the integral of this is going to end up being, and I'm going to write it out in exponential form, or power form. X minus 5 to the 3/2 is going to be 2/3. So 2/3 x minus 5 to the 3/2. Good. And with that, I can start writing out my answer. So my answer is going to be, first of all, uv. So it's going to be x times this times 2/3 x minus 5 to the 3/2. Then I'm going to subtract the integral now of v du. Sorry, so this is my v. So it'll then be v, du is just dx. So now we're dealing with 2/3 x minus 5 to the 3/2 dx. So now I got to take the integral of this. And again, I kind of write it in power function form just because, at least for my mind and in my eyes, this is a lot more convenient to deal with. So again, doing the integral of this is again, what do you call it, a substitution, but it's not much of a substitution. So I'm plugging x minus 5 into a power function, but the derivative of x minus 5 is just 1. So however I do this, at the end, I'm going to be dividing by 1, which doesn't change it. So otherwise, this is a power function. So I'm going to take my power 3/2, I'm going to bump it up 1, which is 5/2, and then I'm going to divide by that. So what this is going to give me then is 2x. Kind of doesn't matter how this is written, but let me write it this way. 2x x minus 5 to the 3/2 over 3 minus, again, that goes up to 5/2, and I divide by 5/2 and by 1. technically. So you end up with 4 x minus 5 to the 5 halves power over what? 5 halves, 15. And all this plus c. And that is my angle. Good. Let's keep looking at some more. So again, just a good instinct. If you have an x there, you probably want that to be your u. Um, yeah, let's look at 27. And let me move the camera. Nope, the other way. Sure. Here we have, actually, now that I'm looking at it, so I'm actually going to slightly change this. I want to make sure this works the way I'm thinking, but let me see. Let me see. Yeah, let me see if I can change it. No, unfortunately, I can't. All right. X cosecant squared x. Yeah, so let's look at something like this. So the integral of x cosecant squared dx. And again, what I see is so definitely two functions multiplied. Notice that this doesn't even fit a substitution form. So if you looked at this and you're like, oh, let me try to find a substitution, well, there's not even a substitution here. This isn't one function inside of another. So this is definitely then, this is a play for integration by parts. And like I was just saying before this on the last problem, notice that you have an x here. So that's again definitely a lead, or that's definitely a signal that that's probably going to be your u. Another thing with this problem, though, so let's think about this problem so that you know it's not substitution. There is no substitution happening. So then it's definitely a play for integration by parts. Let's look at this cosecant squared. Let's think about what could that cosecant squared then be part of with this integration by parts. Could it be a u? Could it be a dv, etc.? So really quick, I just want to dream for a second. What if this was u? So what if u was my cosecant squared x? Um, and so if that's u, if I choose that to be u, then I need to take du. I need to take the derivative of this. And what is the derivative of this? So take a second. We don't have to pause. Just take a second and do that. See if that works. So what do you? So hopefully what you came across is can't even really do the derivative of this. Um, it definitely, so you would have to have, yeah, you'd have to be able to do kind of um, the chain rule with this. So like, sorry, so for one, like in terms of derivatives of trig functions, this doesn't fit any that you guys saw in Cal 1. And then maybe you think chain rule, so it's sort of a power function with cosecant in the middle. I'm sorry, guys. Yes, it does fit. You can't take the derivative of it. Oh, okay. So yeah. So then you kind of look at chain rule, right? And so du here, so this is a power function with a cosecant plugged in into it. And the derivative of cosecant is actually negative cosecant cotangent. So the derivative of this would be 2 cosecant x, but then times kind of negative cosecant x cotangent x. And so you end up with kind of negative 2 cosecant squared x cotangent x. Now imagine plugging this back into, again, our original form. So you're gonna have to take the integral of v du, right? Did this make anything any better, right? Or yeah, so that's not just right, but that's the question. So did this make anything any better for the next integral, the integral we're going to have to take at the end of our integration by parts process? Definitely not. Notice that you essentially ended up with the same thing you started with, but now you have an extra cotangent. So when you go to take the integral of that VDU part, you're basically going to sort of be dealing with this all over again, right? Which is not only just taking you in circles, you know, it's kind of, well, yeah, it's just adding to your complexity. So it's not even just, yeah, it's not even just taking you in circles, it's actually making things more complicated. So looking at this problem, I get kind of gives you again a good practical guideline. If you have an x, you probably want that to be your u. So du is simpler. Notice here that on this problem, you definitely want x to be your u. Also, because making the other part your u makes that the integral of v du much more complex to deal with. So both of those tell me that here this should be my u. That means this is my dv. And really quick, I want you to think through, if this is my dv, then what's my v? I have to take the integral of cosecant squared, and what is that going to be? Good, and hopefully you remember that that's cotangents. So v, it's going to be cotangent. And notice that, again, let's compare that to making that u. Making this u, the derivative was much more complex. You're essentially literally making the function, adding parts to it. Whereas this, taking the integral of this, of cosecant squared, transforms it. One, it transforms it to a different function, and that function is just simpler to deal with, right? Um, um, yeah, just makes it easier to deal with. So for both reasons, this should definitely not be my u. This should be my dv. If I make it my u, the rest of this process is much harder to deal with. If I make it my v, I'm literally, my dv makes the rest of the problem much simpler to deal with. So this is dv, that's my u. V is going to be cotangent x. U is going to be, or du is going to be dx. And we can work that out. So what I'll do is I'll have you guys pause on your side, I'll pause on my side. Go ahead and work the rest of this out. Let's see what we get for the integral. So we're putting it together. This is gonna be okay, cotangent x minus the integral of cotangent x dx. And I believe, so this, by the way, surprisingly ends up being, so when you think about cotangent of x, actually write this out. Now that I think about it, I think we did this once when we were doing the substitution problems, but may not even have explained it much. Or if I did, we just did it once. So let's do it again. Cotangent is cosine over sine, right? Or 5/7, I think this actually might have been it. And so the interesting thing about cotangent ends up being a integration by substitution, and it's kind of an it's both integration by integration by substitution. I guess what I'm trying to say is an interesting substitution. I was trying to say it's a double substitution, but it may not even be that. But it's an interesting substitution. So the substitution here is this is a 1 over x function, or a 1 over function, and what you're plugging in is sine x. And if you think about that, what's the derivative of sine x? That's cosine x dx. So the cosine x dx is just the derivative of what's in the bottom. And you're plugging sine x into a 1 over function. So the integral of this is going to be the natural log of that sine x. This ends up being x cotan x minus the natural log, the absolute value of sine x, all this plus c, and you are good. That is your integral. Let's look at another one. I've done a lot of these, where this is an x. I at least want to we're at least going to look at one where it's not just x. There's also another issue we need to play out. So actually this maybe hits both of them. So let's look at 29. Both issues that I want us to see. So 29 is the integral of x cubed sine x dx. So now we don't just have an x. And so again, we want to think about what's going to be my u, what's going to be my dv, so that, again, my ultimate goal is that integral on the end, the integral of the du is going to be easier to deal with than what we have here. So, yeah, this is where it helps. This is actually a live class or even a remote class. But the question is, what is your instinct here? What should be u and what should be dv? And let's play around with some things, but maybe your instinct is that maybe this is still my u. Because I know if I take the derivative of this, it does make it a simpler function, right? So the derivative of this is 3x squared, so I'm at least making it simpler. Now the derivative is not 1 though, so the big difference we're going to see here is taking the derivative of this and then slapping it on the end of my integral, I'm going to be left with something else to deal with. It's not just going to be a 1. It's not going to sort of disappear. So let's start that way and just play this out and see what we find. So that'll be my dv. So then if this is my u, x cubed is my u, what is my dv? So du is going to be 3x squared dx. Then what is my v? So if sine x is my dv, when I integrate that, what do I get from my v? And that is negative cosine x. Now let's put these parts together, kind of see what we have here. Yeah, I'll go to the side for this one. So my integral of x cubed sine x is gonna be is u times v, sorry, so x cubed times negative cosine x, so I'll just kind of, so it's negative x cubed cosine x, it's fine enough. And we're gonna subtract the integral, so now we have to do the integral of v du. So now negative cosine x, but then I have that times 3x squared dx. Now let's sort of analyze whether this was effective for us. Is this any easier to do than the original integral? Or, first I'll ask that question, see what you guys. And maybe so you're saying yes, and maybe you're saying no. So at the least note that in some sense it's kind of the same, right? I have a polynomial, I have a power function times a trig function, a sine cosine function. So in some sense, I actually didn't change much of anything, right? But then some of you might be saying yes, because at least 3x squared is literally 1 power less than x cubed, right? It's simpler. So and I think you can make an argument either way. So, but I think that's the first thing, is to look at this and realize, wait, did I actually do anything? Is this any better? And I think you can make an argument either way. You still notice that, so basically to do this isn't like the other problems that we just did. So the last three problems where, in the last three problems, when I did the integral of v du, I ended up with just a simple integral. Maybe there's some substitution to it, but otherwise I could handle it really simple. Really, literally the hardest thing you had to do on any of these was maybe 27, where you had to deal with the integral of cotangent vectors. And that was still just substitution. So notice this is not substitution. This is two functions multiplied. There's not one function plugged into another. So the kicker here that I'm seeing with this with the u and the dv that I chose is this is not substitution, which means I'm sort of going to have to do this again. And by this, I mean integration by parts. If I can't do this integral of substitution, then all we know up to this point is that integration by parts is my other play, is my other possibility, especially when you have two functions multiplied. So that, to me, looking at this, I would, so the question, is this simpler? Technically, yes, because it's the 3x squared. But even with it being simpler, the bigger issue is I can't just integrate it. I can't, by that I mean I can't just use substitution and integrate it to be good. I'm actually gonna have to do integration by parts again now with this. And to address probably the first thought in your head, yes, that is hella annoying. So we have an integration by parts where even using integration by parts, I've basically got to do integration by parts again. Now, without maybe writing it all out, or maybe we will write it all out. Actually, we should. Okay. So then the thought is maybe let me switch u and dv. So I want to write this again. Let's switch u and dv, and let's see if we end up in a better place. And the thing is, we might. So part of the reason I want to write this out, kind of, do it again, have us compare and contrast and see which is better, is because, again, you're going to come across problems where combination of functions you see here is just too complex to have a nice, clean, solution method through it. So what I'm saying, again, like I said in an earlier lecture, it necessitates trial and error. So there are just some things that are going to be complex enough that you've got to be okay with trial and error. You can't think that you've done something wrong, or that you're doing something wrong by needing trial and error. There are things that are just complex enough that we need that. So let's trial and error. Let's switch it up and see if we end up with something better. So that's my du now, or dv. Sorry. That's my dv. and this is my u. Now, if that's my dv, I need the integral of that. And if this is my u, I need the du on this. So what I'd like you guys to do, actually, so this, I'll kind of have you guys pause and I'll pause on my side. I want you to figure out dv for x cubed, du for sine of x, and then put those pieces together and just kind of sit there, and we're gonna come back and compare the two and see which is better to deal with. So go ahead and pause on your side. All right, good. X cubed is my dv, the integral of that is gonna be, so v is gonna be x to the fourth over 4. And then if this is my u, if sine x is my u, then my du is cosine x dx. So really your v was x cubed dx. Sorry for that. Good. And with that, then when we put this together, my integral would be x to the fourth over 4 sine of x so uv minus the integral of now v du. So x to the fourth over 4 cosine x dx. So this is another possibility for doing this integral. So now what I want to look at is compare and contrast. Which one is better? So what do you guys think? And again, there's probably some arguments to be made either way, but notice that basically my powers are higher here. So the nice thing is I don't have to mess with this anymore, but then I'm gonna have to integrate this. So looking at this integral, you're running into the same issue that you have with this integral, that you're still this is not substitution, it's gonna have to be integration by parts. And now if I do basically sort of the same scheme, if I choose this is my dv and this is my u, this is gonna keep getting higher. So we're gonna basically, so what you want to start doing and comparing these and which one is kind of the better approach is you want to think about kind of if you kept doing the same thing, so sequentially, pattern wise, what would happen? If I kept doing the same thing, the problem on this approach is we get x to the fifth and then x to the sixth. And then so you keep getting kind of higher powers, whereas this, if I keep doing the same approach, which is the polynomial is my u and the trig function is my dv, then at least I'm going to get lower powers. We've still got to play this all the way through, so we've got to choose one of these ways to go at it. But I think, at least for now, hopefully that makes sense to you, that this is maybe the better approach. So the first thing to notice about these, though, is it doesn't solve the fact that you're going to have to do integration by parts again. Whichever way you do this, you're going to have to do integration by parts again. But at the least, this method edit is giving us lower powers, which gives us just a simpler function relatively. So another way to kind of think about this is, so again, if we continue the pattern we see here in our choices of our u's and dv's, so this next iteration will end up with a lower power, and then if we have to do it again, we'll end up with a lower power. At some point, we're going to get this down to 1, right? Or to x. And once we got this down to x, then we pick that for u, and the derivative is 1, and then that final integral is you're going to be able to do it. The other issue with this is that if I keep picking this as my dv, I'm never, basically this process, at least in terms of thinking about the polynomial, it's never going to end. The next one's going to be an x to the fifth, and the next one's going to be x to the sixth. I'm going to have to keep doing integration by parts over and over again. Now, technically, the trig function is going to make it so that in this case, you wouldn't do it infinitely. But in general, that's going to be one of the problems you're going to see with once the x has a power larger than 1, is if you pick the polynomial as your dv, you're going to keep getting this end of your integration by parts that has a higher power, and you're basically never. So theoretically, if this, I mean, you'll see how this problem plays out, but if this wasn't a sine x, this was something else, then you would end up with an infinite haul of integration by parts, with integrals at the end that you're going to have to do, and it would never end. Way later in this class, actually, but basically way later in this class and in another class, you would actually see that there's a way to represent functions with those infinite halls of integrals, that is actually useful, way, again, at the end of this class and in a way later class. But in terms of trying to find an integral, it's not useful at all, right? That if I have to keep integrating this and then integrating this and then integrating this, and these powers keep getting bigger, and it never basically, in my mind, the way I think about it, it never settles down. Never settles down to something that you can just cleanly take the integral of and be done with. Then that's not going to work for us. That kind of sucks, right? So overall, comparing these, I'm definitely going to go with these choices, with the x cubed being my u, sine x being my dv. At the least, this will eventually settle down. So again, even without the cosine, the sine and cosine, if that was a different function, at the least this would settle down eventually to an x, and so I'd end up with an integral at the end that I could work out. So, so I'm going to erase this, and let's keep playing this. All right. Let's see, and this is a minus of minus, so what I'm going to do here is I'm going to make that a plus, and just take away the minus so we don't have to deal with extra minuses, pluses, coefficients, all that kind of stuff. So now I have cosine of x times 3x squared. So again, what I'm going to do, so back to my point though, before we did that, looked at that second option, the kicker here is that this is not substitution. You have to do integration by parts with this. And so I'm going to make the same type of choice that I did on this one. I'm going to make that my u, and I'm going to make this my dv, and I'm going to then do du, I'm going to do v, so what I'd like you guys to do is figure out your du and your v here, and then what you're going to have to do is rewrite all of this. Just like you rewrote this integral as this, you're now going to have to rewrite this integral as using integration by parts. So see if you can do that. Pause on your side, I'll pause on my side. Let's see if you can do that. All right, let's see what you got. So when you take the derivative of 3x squared, what did you get? Good, that's going to be 6x. And when you take the integral of cosine x, what do you get? Sorry, 6x dx. When you take the integral of cosine x, what do you get? So that should be sine x. So now let's put these pieces together. So I still have this negative x cubed cosine x. That is still there. But now when I do the integral of this, I have to rewrite this as integration by parts. So that is going to be u times v. So now it's plus 3x squared sine x minus integral of b du minus the integral of sine x 6x dx. Good. So now I have kind of these two pieces and I have this integral. Now I want to look again, can I do this integral? Hopefully simply. Simply. So what do you guys think? So looking at this, is this a substitution? Can we do that using substitution? And so hopefully, and also unfortunately, so you may be weeping inside a little bit, and that is the appropriate response here. Looking at this, you'll notice that again, I can't do substitution. This is still just a function times a function, so I'm gonna have to do integration by parts again. So there are some problems like this where this is just the nature of it. It's just kind of is what it is. Again, there are things complex enough that we don't have nice simplifications. Maybe one day we will, so there's, I would say, a philosophy or, a way, philosophy is not the right word, but some people who work with science, math, logic, there's sort of a, it's like worldview is not even right, but I made it similar to worldview assumption. There's sort of a assumption, a worldview, an assumption that if we can keep simplifying things and finding patterns, if we can keep finding patterns, we can keep simplifying things, basically. And then I think there are others that think that, there are just parts of our reality that are sufficiently complex that we're never really going to simplify. Like, again, maybe we find a pattern, but it's still not going to necessarily simplify it. And philosophically, logically, that's a good debate, actually, between those two worldviews. Can patterns, if you see enough patterns, can you simplify everything in the universe? Or if you see enough patterns, are some things still going to be complex? And we don't know the answer to that. So that's a random philosophy insert. But meanwhile, before we figure that out about reality, meanwhile, this is still complex and we're going to have to do integration by parts again. So now we want to pick our u and our dv on this part. And so that's interesting because I think I'm thinking of a different function that has a different behavior. I think of sort of the behavior of the overall problem. In my mind, there's actually patterns to these overall problems, the way they play out. And I thought this was one pattern, but it is not. So again, I want to make a similar choice because again, notice that, so I'm going to have to do integration by parts again, and that sucks. And I'm weeping inside, and I should. But at the least notice that 6x sine x is simpler than 3x squared cosine x. So back to one of those original questions I asked you about this program, or about this problem, the matrix. What do you call it? Are we in a simulation? I don't think so, but it's a decent argument. It's a decent argument either way. So anyway, sorry. Random inserts on Bruce. My mind is ultra swirling. Anyways, one of the original questions I asked you about this problem after we did this is basically, was this any better than the original integral? And we sort of said, well, maybe not because it's the same thing. It's a trig function times a polynomial, but at least that polynomial is simpler, right? So the overall arc of this problem, what I have done, even though I've had to do integration by parts again, and I'm gonna have to do it again, I at least have made the functions I'm dealing with technically simpler. I had an x cubed, now I have a lower power function, now I have a lower power function. And that matters because that tells me there's at least gonna be an end to this process. If I do this again, I'm gonna probably then end up with an x. And then if I do that again, maybe, then I'll have an integral I can finally take, right? So again, that's your overall arch to these problems is you need to make your choices so this end integral is at least easier to deal with or at least simpler. So I'm gonna make the same choice then. I see a pattern. I went from x cubed, 3x² to 6x. So something is working here. Something is happening. I'm gonna again choose this to be my u, this to be my dv, and we'll work from there. So what I want to do is let me just kind of take this forward for you guys. Du here. Oh, actually no. Yeah, wow, give me some teacher debate in my head. Well, okay, let me have you guys do this. So let's be piece by piece, kind of clunky, but I think this will work well for you guys to actually work this out as we go and kind of practice the parts. So I'm going to choose that to be my U, this to be my dV. So I need you guys again to figure out the V. I need you to figure out the du, and then I need you to rewrite this out, this part out, this integral out using integration by parts. Let's see what we get. So go ahead and pause on your side and I'll pause on mine. All right, so your V here, dV was sine x, so what did you get for V? Good, taking the integral of that, you're gonna get negative cosine x. And your du, so 6x dx was my u, so what's my du there? Good, that's gonna be 6 dx, 6, derivative is 6. So then, what I have is negative x cubed cosine of x plus 3x² sine of x. So that's the legacy part of that problem from the previous two steps, previous two integration by parts. Then it's gonna be minus, and now it's gonna be the integral of it's gonna be uv. So u times v, so 6x, so negative 6x cosine of x. And then minus the integral now of v du, so negative cosine x times 6 dx. So I'll just and let me work out a couple signs there. Let me see. So this is gonna be negative x cubed cosine of x plus 3x² sine of x. It looks like I have plus 6x cosine of x. And then plus basically the integral of 6 cosine x dx. Good. And notice I still have an integral to do. But what's different about this integral? Good. This is actually a simple integral I can do. So I no longer need integration by parts. And again, the key here is we got down to a point where my u was an x. So I knew my derivative was going to not involve x anymore. It was going to be a 1, which means that integral is something I can do. So again, not just conceptually, but strategically, practically, that's the goal of your problem, your choices of u and dv to begin with. By choosing u to be the polynomial, even though it took several integration by parts, several rounds of integration by parts, I was able to eventually get down to an integral where the x wasn't there anymore. And what is the integral of 6 cosine x? We'll just do it really quick. This is easy. Well, actually, no. So we won't even pause. So I'll give you guys a second. Go ahead and find the integral of that, and then let's kind of round this up and write the final answer up. Oh, integral thick cosine x, what are y'all getting? The integral of that goes back up to sine. So what I see here is you end up with, basically it's gonna be six sine x. So negative x cubed. So finally, negative x cubed cosine x plus 3x² sine of x plus 6x cosine x plus 6 sine of x sine of x. No, we don't need a dx. All plus a c, and we are done and good. And if you really want to be, if you really want to do a little extra with this, then you can group together your like terms. Completely not necessary. But if you did that, this would end up looking like, so really quick. So, what? So we have two different ones with a cosine x, so we'd end up with negative x cubed plus 6x times cosine x. And then we have two of them, or you can write 6x minus x cubed, and then we have two of them with a sine x, so plus 3x² plus 6 times sine of x. And that is another way to write that same thing. And so there are going to be problems like this. Just choose your U and your dv or your scheme for picking those smartly to begin with, so that even though you have to keep doing integration by parts, you want to hit this point where there's an end. So again, going back to that alternate choices that we tried out for a second on here. Imagine if we did have the alternate choice. Your powers would have kept getting bigger and you would have just never ended. You would have been taking integration by parts for the rest of your life, and into infinity, right? It would have never ended. Now, I do really quick want to note that you can prove mathematically that infinite sequence, basically, of that you would have got using the other choices is actually mathematically equivalent to what we see here. But I just want to throw that out there. Don't even want you guys to maybe try to think about that or justify that in your head. That requires a ton of conceptual, theoretical, not just algebra, but some other stuff that we have no way to approach here. But it's technically mathematically equivalent, but it's also weird, complex, and there's no reason you'd ever want to write it out that way. This is the answer. This is the better way to write it. All right. And actually, let me look. Actually, for this section. Well, is there one more we should look at? Yeah, there's one more we should look at here. But there's good reason for this. So there's one more we're going to look at. And we need some amount of space. Let's see. How far can you guys see on the board? All right. Let's see if we get a little. I think that would still be fine. So let's look at 33. You guys can see that. Let's talk our way through this problem. So let's look at taking the integral of this. Now we've been choosing all these problems before that we basically had a polynomial, especially just at x, as one of our functions we were multiplying by. And we just chose that for u because again, it was convenient. Even like on the last one, it was eventually convenient, right? It eventually got us to a 1. We could take that integral very easily. Notice here, so I have an e function times a, what do you call it, a trig function. Now the sine of 5x, you can imagine it's kind of act like the sine of x on the last problem. So if I choose this as dv, like we did on the last problem, like I think we're probably not only used to, but we're inclined to, it's going to act like the last one where get a cosine, and then if I have to do integration by parts again, I'll get back to a sine, I'll get a cosine, sine, etc. But notice, let's think about this e to the negative 3x, and let's say we did choose this to be u. Are we thinking about choosing this to be u? Does it act the same? So think about taking the derivative of it and its overall act, like the transformation of that the function to its derivative, and if we have to do it again, that to its next derivative. Does it act the same as a polynomial as a power function, as the x? Good. And hopefully in your mind, you kind of see the shape of that it doesn't act the same. So it doesn't act the same. A x, take the derivative and you get a 1, and essentially that goes away. And even if you start with some higher power, an x cubed, like we did in the last problem, it was a 3x squared, and then a 6x, and then a 6. And we're good, right? But in exponential function in general, e to a power, you take the derivative and you get e to the power. You take the derivative, you get e to the power. So again, it's the one function that essentially stays the same, minus coefficients, whether you take the derivative or the integral. So essentially, like, basically it doesn't move. So it doesn't change, it doesn't move, it stays an exponential function. So the first thing to note is if I'm going to choose this as u, it doesn't give me that advantage that I was not only used to with power functions, but I was really relying on. I was relying on the power functions, the power going down, and eventually getting to just a coefficient. That is actually what helped me do the integration by parts on all the previous points. I don't have that advantage here. So then the next legitimate question, again, you're trying to think your way through this problem before you just kind of blindly try things. You're still going to need some trial and error, but you want smart trial and error. So the next question is then, should I even choose it as u? And so maybe not, and maybe I choose it as dv. Again, the thing to think about, I will say one nice thing about the e to the x function is, and then if you think about taking the integral, so let's think about taking the integral of e to the x, what does that give us? Still gives us e to the x, right? So again, e to the x is a special function where basically derivatives and integrals don't, minus constants, coefficients. Derivatives and integrals don't change it a lick. It stays the same function. So actually, it doesn't actually give us any advantage to really choose it as dv or u, because it's really going to do the same thing either way. So you can choose it to be whatever you want. I'm going to go ahead and choose this as u, just because I'm used to sort of the thing on the, that thing on the left being the u, and I'm going to choose this as dv. And let's look at what we come out with. So let's figure out what du is, and let's figure out what v is, and then let's go ahead and run that through integration by parts. So all pause on my side, you do the same on your side, and work that through. So e to the negative 3x to u, and du is going to be negative e to the negative 3x dx. If sine of the 5x is my dv, then you integrate that up, and what you should get there is 1/5. Actually, negative 1/5 cosine of 5x. That's just again kind of simple substitution work there. So So if that's our u's and v's and du's and dv's, then integration by parts says the integral of this is u times v. So it's going to be negative 1/5 e to the negative 3x cosine of 5x minus the integral of v du. So I'm going to make this plus since it was already minus. So plus 1/5 cosine of 5x. And actually, well, yeah, du is also a negative, so I guess that spins this back to a negative. Minus 1/5 cosine 5x e to the negative 3x. Yes. Again, hopefully you'll be inside. Hopefully, but should be moving inside again because again we're stuck in a situation where so our choices for u and dv, just as a short so we can get through the rest of this lecture, we're fine. But we're gonna have to do integration by parts again. This is not looking at this integral. This is not substitution. So we're gonna have to do this again. So again, there's gonna be problems like this where it's just the way the patterns play out. It is necessary to keep doing integration by parts till you sort of reach an end. Or at least on this last one we reached an end. So I wanted to show you this problem because this one doesn't reach an end, but in a different way than the previous problem. So they structurally, pattern-wise, overall in a different way. But like the last problem, so if you make good choices for u and dv, you still end up with this integral being an integration by parts that you got to do. Keep the same pattern in your choices of u's and dv. So I would say that's another good rule of thumb or way to play out integration by parts. So if you end up in this situation, you know you're gonna have to do the integration by parts at least again, if not maybe multiple times. Keep picking your u's and dv's in the same pattern. So that we saw in the last one that's actually what got us to the end, is we kept picking the polynomial as our u, we kept picking the trig as the trig function as our dv. So keep picking the same pattern so that it's in some sense what you're doing literally is, again, if you're trying to visualize the pattern of the problem, not the particular elements, the particular functions, but what's happening overall to the problem, you'll just try to visualize it. If you flip-flop which types of functions you're picking for your u's and your dv's, then in some sense, your problem's going to sort of go all over the place algebraically. But if you keep picking the same types of problems for your u's and same types of problems for your dv's, you're going to have a clear pattern algebraically that, again, hopefully will resolve itself at some point. So let's see so like I said, this one, you're gonna have to keep doing integration by parts and it will come to an end, but it's gonna come to an end in a different way than 29. So let's see how it comes to an end here. So I'm gonna continue my pattern where I pick my e function as my u, because again, taking the derivative integral that I still get an e function. So that's gonna be my u, and I'll figure out the du on that. And this is gonna be, including the dx, my dv. And I'll figure out the v on that. Actually, give me a second. I'll make sure this is going to work out the way that I thought it was going to work out. So it probably just goes back. Well, let's play this out. So again, what you'll need to do is figure out your tu and your v, and then you're going to have to put that together into replace this with the next iteration on your integration of parts. So I'll pause, you pause, go ahead and do that, and then we'll come back and see where we're getting. All right. So your v here. So this is my dv. My v, again, I'm gonna be integrating, so I'm gonna be integrating up. So cosine is gonna go back to sine. I'm gonna divide by 5 again, so I'm gonna end up with 1/25. Now sine of 5x. My du, e to the negative 3x. Notice it's the same it's the same u and du that you had on what do you call it, the first integration by parts that you're doing there. So negative 3. You know what, guys? I'm sorry. On this original du, sorry guys, making a bunch of mistakes today. That should be a negative 3 e to the negative 3x. So that's going to change a couple things here. That'll make this negative 3/5 e to the negative 3x. That'll also make this basically a 3/5 there. So now this is going to do 3/25. All right, but let me write this correct. So negative 3 e to the negative 3x dx. So then when you put this together, I have negative 3/5 e to the negative 3x cosine of 5x. Then minus, so u times v. You guys understand the positives and negatives here, so I'm just gonna write them out as they should be. So minus 3/25 e to the negative 3x sine of 5x. And then minus a minus, so it's plus, and then we're doing v du. So actually it's still a minus the integral of now 9/25 sine of 5x e to the negative 3x. And give me a second, guys, to remember there's a little bit of an outbreak trick from here. Let me just give me a second to remember this. Oh, yes, that's the outbreak trick. Okay, sorry, guys. All right. Now, so you get this. Now we notice that we again have integration by parts. And I will say that it seems like then this is going to keep going on forever because we now have to do basically, notice that we basically have to do the integral all over again of sine of 5x e to the negative 3x, the original integral we started. So it seems like we are literally going in circles. We have to do this again, and we'll have to do this integral again, and we'll just have to keep oscillating back. However, so I've been doing, all of this is solving this integral of e to the negative 3x sine of 5x, right? And so, so what I'm going to do here is I'm going to write, so what I'm saying is e to the integral of e to the negative 3x, give myself a little more room, the integral of e to the negative 3x sine of 5x so far equals this, sort of this integral that I haven't resolved yet. But notice that this integral is the same as this. So in some sense, like you literally can think of the integral of e to the negative 3x sine of 5x as its own variable, and I've got one of them over here, and I've got negative 9/25 of them over here. So what we're going to do from here is instead of just keep doing integration by parts and going in circles, I'm literally just going to add this onto the other side of the equation. And then isolate the integral of e to the negative 3x sine of 5x. So from here, you actually algebraically can stop this process, and otherwise we just take you in circles. So again, on the last problem, you eventually had, sorry, so on 29, you eventually had one last integral that ended, right? That you were able to do. Here, if we keep doing this, we're just going to keep getting, we're going to get this integral, we're going to get this integral, the next iteration of integration by parts, and then we'll get back to this with a different coefficient, etc. And you're going to keep bouncing back and forth between them, but you won't ever actually be able to finish that integral. So instead of playing that out, let's just add this to both sides. And if I do that, then what this ends up being, so I'm gonna end up with 34/25 times the integral of e to the negative 3x sine of 5x equals everything we have there minus that cancels out. So negative 3/5 e to the negative 3x cosine of 5x minus 3/25 e to the negative 3x sine of 5x. And then notice that if I just divide by, multiply by 25 over 34, divide by 34 over 25, it's the same thing. But basically, if I just clear the coefficient off, then I've got my answer, because then it says the integral of this equals, and now we got everything on the right will involve an integral. We won't have that infinite kind of hallway of integrals to do. And so that's all we do here. So divide by 34/25, both sides, etc. You guys kind of get the idea. So what this gives us overall then is the integral e to the negative 3x sine of 5x. That has to equal 25 over 34. And so on the first one, it's going to be, what, 5's actually, 5's cancel. Negative 15 over 34. Yes. 15 over 34 e to the negative 3x cosine x. Then minus 3/34 e to the negative 3x sine of x. All plus c. There you go. Plus c on this one as well. And that is my answer. You end up with sort of this, finishing the integral of this, you end up with sort of this pair, e to the negative 3x times cosine x, e to the negative 3x times the sine x, and you have these coefficients that pair in front. And spoiler alert, you get to a differential equations class later, it's forms like this where you kind of have sort of this prototypical like two parts that are slightly different with coefficients from them, end up being pretty typical solutions to a lot of differential equations. So you're going to see some problems that kind of, again, the overall arc of the problem, the way it plays out. You can sort of picture that in your head, or at least think through it visually in steps. Kind of plays out like this. So we would have ended up in an infinite circle, but we're able to just use some simple algebra to stop that circle. Good. And that will actually handle all the problems that you guys can see. Again, in general, the overall arc of the problems is going to end up like, either the initial type that we saw for several in a row, or what we saw in 29, where you have to do multiple integration by parts, but there's sort of an endpoint. There's a last integral that works, or something like 33, where it would end up in an infinite circle, but you use simple algebra to end that. And that'll be it. So you guys can go ahead and knock out section 8.2. We'll come back for the next lecture. Should be 8.3. I'll see you guys then.